Hi everybody, and we're going to now do the final part of our curve sketching for quartic function. If you remember in the last video, we went to great lengths to create this interval table that would identify the critical components of our function. And if I can remind you and refresh your memory, the function we were dealing with was this function that you see at the top of your screen right here. And now our job is to put all that information together and try to come up with a realistic picture of that function, and then maybe also just graph it using technology. So if we put everything together, let's see what we have. We'll write it down and then we'll go and use it. So the x-intercept value was 0. And it actually, the ordered pair was 0, 0, because the y-intercept was also 0. So the x-intercept was 0. The end behavior of our function was that as x approaches infinity, y approaches infinity. And as x approaches negative infinity, y approaches positive infinity. Okay, what else? Our chart indicated that we had a minimum occurring at the place where x was equal to 0. Okay, so minimum at x equals 0, and the ordered pair we know for that is 0, 0. Our chart also indicated that we had a point of inflection occurring at the place where x was equal to 1. And importantly, the point of inflection did not have a 0 slope, okay? Like if you look at where the place where x equals 1, and you examine the slope of the function at that point, right? Sorry, the slope of the function at that point, it's a positive slope, but there is 0 concavity. So we have a point of inflection, POI, at x equals 1. And if you plug x equals 1 into the original function, what you find is the actual ordered pair is 1, 11. We also have, according to our chart, a point of inflection at x is equal to 3. But this point of inflection is characterized by a 0 slope for x. Okay, if you see remember the derivative function would indicate that there's a 0 slope for x at the place where x equals 3, but since the slope of the function doesn't change over that interval, it's not a turning point, it's just a point of inflection. So we can go down and let's just make sure that we put in that relevant point, because it is very important. So we also want to say that we have a point of inflection at x equals 3, but this point of inflection we want to make a mental note of has a 0 slope attached to it, and the actual ordered pair for that particular point is 327. 327. Okay, so just a rough sketch of the situation then. We have x-intercept at 0. We have a minimum at 0. We have a function that is concave up from negative infinity to 0. We then observe from our chart that the function has positive slopes to the right of 0, and that it reaches a point of inflection at 111. So we'll just go ahead and we will now turn our graph upwards, and we will see that it will have a point of inflection, which we'll just, for argument's sake, here, let me do that again, make that a little neater. We'll just say something like that. After the, and you know what, we'll just put a dot there. We'll just indicate that that was our point of inflection right there, okay? And then after that point, after 1, the slope remains positive but the function becomes concave down, okay? As witnessed on the interval from 1 to 3, the function becomes slightly concave down. So for our purposes, therefore, that means that the function begins to look something like this. Then at 3, at x equals 3, the slope bottoms out. We get a flat slope, okay, as witnessed here in our chart. Where you see with x equals 3, the slope is 0, okay? And okay, the second derivative also turns out to be 0, but we'll see the significance of that. But then after 3, the slope turns positive again, so it remains positive, and then the function becomes concave up. So what does that look like? That looks like this. We get a 0 slope. Let me move that up a little so you can see. We get a 0 slope, and then it goes concave up. Okay, and that point right there, okay, so like right there, and right there, those are our key values, right? And the value, you know, like here, 0, 0, here we got 1, 11, and here we got 3, 27. Right? And this should be how our graph generally looks. Why don't we verify that on Desmos? So let's go over to a Desmos graph and just put that in and see if we can come up with anything that remotely resembles what we believe to be is the situation. So I'm just going to try and do my best to open up a Desmos screen. And I think we've got it going here. Okay. And so I'm going to type in my function, which is x to the power of 4 minus 8x to the power of 3 plus 18x to the power of 2. And then I think it's really important that I change my settings, right, so that we can see the full picture of the graph. Why don't we go, we don't need to go below the y-axis, so let's just go like for the y-axis, let's go our minimum value like -5. But then for our maximum value, we want to go right up to like 40 or something, so we can clearly see, because those critical values for y were occurring. And then, yeah, I think that's good. And you know, I think that should be good. Let's see. There we go. If we click on some key points, we can see that we got 327 here. Let's write those in so we can, so 3, 27, there it is right there. Okay. 1, 11, there it is right there. There's our point of inflection where the graph transitions from being concave up to concave down. And then of course 0, 0. Okay, which is our minimum right down here. Oops, I see that. Okay, and so what you see, guys, is you see the benefit and the power of calculus, because remember, advanced functions would have a very difficult time identifying this little tweak in the graph that you see here at 327, but calculus will let you do it. I hope you found that helpful, and I'll give you a follow-up question to try.